In the vast, dark expanse of the universe, there are objects so strange they defy our everyday understanding. They are places where gravity is so strong that nothing, not even light, can escape. We call them black holes. For decades, these cosmic enigmas have captured our imagination. They represent the ultimate frontier of physics, a point where our best theories about space and time seem to break down. When we look up at the night sky, we see stars and galaxies, but we are also peering into a cosmic ocean filled with these invisible, powerful objects. They are the ghosts of massive stars, the silent engines at the heart of galaxies. When most people think of black holes, they often picture them as giant cosmic vacuum cleaners, relentlessly sucking up everything in their path. While it's true that their gravitational pull is incredibly powerful, this popular image doesn't tell the whole story. They are born from the deaths of the most massive stars in the universe. When such a star runs out of fuel, its core collapses under its own immense weight-crushing matter, down into an infinitely small point called a singularity. This collapse creates an object so dense that its gravity warps the fabric of space-time around it, creating a region from which nothing can escape. As gas, dust, and even entire stars get too close, they are pulled into a swirling, superheated disk of matter called an accretion disk. The friction and intense gravitational forces in this disk heat the material to millions of degrees, causing it to glow brightly with X-rays and other forms of radiation. In fact, these accretion disks are some of the brightest objects in the cosmos. The notion that a black hole could be used as a source of energy sounds like something lifted directly from a science fiction novel. Yet this idea has its roots in serious theoretical physics, dating back to the work of brilliant minds in the 1960s and 70s. The physicist Roger Penrose, who won a Nobel Prize for his work on black holes, first proposed a mechanism for extracting energy from a spinning black hole. He imagined a civilization advanced enough to lower an object into the region just outside the event horizon, and then release part of it into the black hole. Through a clever trick involving the black hole's rotation, the remaining part could be retrieved with more energy than it started with. This theoretical heist, now known as the Penrose process, was a landmark achievement. It proved in principle that energy extraction was not forbidden by the laws of physics. Two researchers, William Press and Saul Tucholsky, took this concept a step further in 1972. They wondered what would happen if you didn't send a physical object, but instead sent waves towards a spinning black hole. Their calculations led them to a remarkable and related phenomenon, which they named superradiant scattering, or simply superradiance. With the physics of superradiance established, Press and Tucholsky took their idea to its logical and most explosive conclusion. They imagined constructing a giant, perfect mirror that completely surrounded the spinning black hole. This mirrored sphere would act as a resonant cavity, trapping any waves between its inner surface and the black hole's event horizon. This seemingly simple addition to the scenario would have catastrophic consequences, turning a gentle process of amplification into a runaway chain reaction. Here is how their theoretical bomb would work. A single low-energy wave is introduced into the cavity between the mirror and the black hole. The wave travels towards the black hole, enters the ergosphere, and is amplified by superradiance. It then travels away from the black hole until it hits the surrounding mirror. With each round trip, the wave's energy grows not in a linear fashion but exponentially, doubling and redoubling in a feedback loop of unimaginable power. The energy inside the mirrored cavity would build up at a terrifying rate, all of it being drained from the black hole's rotation. Eventually, the energy would reach a critical point where the mirror could no longer contain it. The mirror would shatter, releasing all the accumulated energy in a single gargantuan explosion. The power of this blast would be astronomical, potentially releasing more energy in an instant than a galaxy of stars. To truly grasp the radical idea of a black hole bomb, we must first understand the black hole itself. What is it really? At its heart, a black hole is a region of space-time where gravity has become so overwhelmingly strong that it creates a one-way door in the universe. At the very center lies the singularity. This is the point of infinite density, where all the matter that has fallen into the black hole is crushed. Surrounding this point of infinite mystery is the event horizon. This isn't a physical surface you could touch, but rather an invisible boundary, a point of no return. Think of it as the edge of a waterfall in a river. If you are in a boat far upstream, you can paddle away. But as you get closer to the edge, the current gets stronger. Once anything, including light, crosses this threshold, it can never escape the black hole's pull. For a spinning black hole, this region is called the ergosphere. It is a place where the black hole's rotation is so powerful that it drags the very fabric of space-time around with it. Within the ergosphere, nothing can stand still relative to a distant observer. Everything is forced to rotate along with the black hole. This is the crucial area where energy extraction, the key to the black hole bomb concept, becomes theoretically possible. The giant mirror in the classic thought experiment is a clever theoretical tool, but it is also the most artificial part of the scenario. Could nature provide its own mirror and trigger a super-radiant instability? Certain theories suggest the existence of ultra-light particles, such as hypothetical particles called axions. These particles would have a very specific property. Their quantum wavelength could be huge, comparable in size to the black hole itself. If a spinning black hole is formed within such a cloud, or if it drifts into one, the conditions for a super-radiant instability would be met. The black hole's spin would naturally amplify the axion field itself. The black hole bomb, in its natural form, is no longer just a wild theoretical idea confined to chalkboards. It has become a tangible prediction that we can actively search for in the cosmos. If these natural bombs, powered by clouds of ultralight particles like axions, are really going off, they should leave a distinct signature. The most promising signal would not be a flash of light, but a burst of gravitational waves. Scientists are meticulously sifting through the data these observatories collect, looking for faint, long-lasting humming sounds in the gravitational wave spectrum. While we cannot travel to a real black hole to study superradiance directly, physicists have devised incredibly clever ways to test the underlying principles here on Earth. In 2017, a team of scientists in Scotland conducted a landmark experiment using sound waves. They created a rotating vortex of fluid and sent sound waves towards it. They were able to demonstrate that the sound waves scattering off the spinning vortex were amplified, carrying away more energy than they came in with. The story of the black hole bomb is ultimately a story about the scientific process. It began with a simple question born of curiosity, which led to a mind-bending thought experiment by Roger Penrose. Decades later, this abstract idea has blossomed into a concrete research program, with scientists around the world actively searching for the evidence that could turn this theory into a reality. This journey is far from over. Our gravitational wave observatories are becoming more sensitive with each passing year, opening new, clearer windows onto the gravitational universe. What we learn from this quest will undoubtedly reshape our understanding of the cosmos. If we find evidence for superradiance, it will confirm one of the most exotic predictions of general relativity and open up a new chapter in black hole astrophysics. If we find the signature of a natural black hole bomb, it could reveal the existence of entirely new particles and forces, revolutionizing our understanding of fundamental physics. Ultimately, the story of the black hole bomb is a story about the relentless human drive to explore the unknown. Black holes are nature's ultimate puzzle, and the black hole bomb is one of its most intriguing clues. It reminds us that there are still great mysteries to be solved, vast territories of knowledge yet to be explored. Our journey into the unknown is what defines us as a species, and the enigmatic darkness of a black hole is one of the most compelling destinations we can imagine. And so, we continue to peer into the abyss. We do so not out of fear, but out of a profound sense of wonder and a relentless desire to know.